In this session, we focus on the container reshuffling problem, also called remarshalling. It is the day-to-day reality of container yard rehandling. Extra moves that do not create customer value, but are required just to reach the container you actually need. When a requested container is buried inside a stack, the yard crane has to temporarily move blocking containers out of the way. Those moves consume capacity that could have been used for vessel loading, truck service, or productive rearrangement. Reshuffling occurs when the target container is not at the top of its stack. Blocking containers must be moved out temporarily, the target is retrieved, and then the yard must decide where to place the displaced containers. The operational objective is to reduce unproductive moves while maintaining feasible yard operations. That means you want fewer relocations, but you still have to respect how the yard actually works. Limited stack height, limited space, and time-based retrieval needs. Consider Rotterdam, handling over 15 million 20-foot equivalent units per year. In the scenario, a vessel arrives with 2,000 containers for multiple inland destinations, and the yard stores them using automated stacking cranes. Later, truck arrivals trigger retrieval requests that may not match the original stacking order. That mismatch is the root cause of reshuffling. The container you need now may be under containers you will need much later. Each reshuffle consumes crane time, fuel or electricity, and equipment lifetime. It also creates operational ripple effects by delaying trucks and increasing downstream transportation cost. Studies indicate reshuffling can be about 20 to 40% of total yard crane moves in large terminals. When that share is high, the yard looks busy, but much of the work is simply undoing earlier stacking decisions. This deck is organized as a tiered toolkit. Tier 1 provides the mathematical foundation. Tier 2 introduces a minimum blocking heuristic. Tier 3 adds a genetic algorithm. Tier 4 uses reinforcement learning with a deep queue network. Then Tier 5 expands to an integrated digital twin. Tier 6 moves to an autonomous multi-agent ecosystem. And Tier 9 frames the same optimization challenge for quantum optimization with the quantum approximate optimization algorithm. Tier 1 models reshuffling as an integer program. The decisions represent where each container sits over time and whether it must be reshuffled. The goal is to minimize the number of reshuffles while keeping the yard feasible. Feasible means containers are placed only after they arrive, stacks never exceed capacity, and earlier retrievals are not trapped under later retrievals without paying a reshuffle cost. This slide introduces the sets used in the formulation. These sets define the objects the model reasons about, including containers, stacks, and time periods. Operationally, sets are the model's scope boundary. If a container, a stack, or time period is not in these sets, the model cannot track it, constrain it, or optimize it. Containers are the physical items being stored and retrieved. Stacks represent yard stacks or stack lanes with limited height. Time periods represent arrival and retrieval windows. This makes the model explicit about when and where blocking can happen. A blocking situation is not just about location, it is also about timing, what you need earlier versus later. This slide lists the parameters used in the model. Parameters capture facts the optimizer must respect, such as stack capacity limits and the timing information for each container. Operationally, parameters are the fixed inputs from planning systems and operational constraints. If the parameters are wrong or missing, the model can look correct while producing plans that fail on the ground. Stack height limits enforce physical feasibility. Arrival times define when a container becomes available to stack. Retrieval times define when the container must be accessible. The mismatch between arrivals and retrievals creates reshuffling pressure. The more uncertain or changeable the retrieval sequence is, the more value there is in placements that reduce future blocking. This slide defines the decision variables. These variables represent placement choices, blocking indicators, and reshuffling indicators. Operationally, variables turn a real yard into a controllable plan. If you cannot represent a placement, you cannot enforce it. If you cannot represent blocking, you cannot detect it. If you cannot represent reshuffling, you cannot minimize it. Without placement variables, you cannot represent yard state over time. Without blocking variables, you cannot detect when one container sits above another. Without reshuffle variables, you cannot count and minimize unproductive moves. The model would then be optimizing a simplified world that does not include the operational pain you are trying to remove. This slide presents the objective. In this formulation, the objective is to minimize the total number of reshuffling operations. Operationally, that objective aligns with throughput and cost. Every reshuffle consumes scarce crane capacity and creates delays, so reducing reshuffles is a direct lever on performance. The objective counts how many times containers are reshuffled. Every reshuffle is a non-productive crane move that reduces throughput. Minimizing this quantity directly targets operational waste. It does not guarantee zero reshuffles because some reshuffling is unavoidable under uncertainty, but it pushes the plan toward configurations that keep near-term retrievals accessible. This slide introduces the container placement constraint. It enforces that each container must be placed within its feasible time window. Operationally, this prevents impossible solutions, where a container is used before it arrives, disappears from the yard, or is duplicated across multiple stacks. Each container must be placed exactly once between its arrival and retrieval. This prevents impossible solutions that use a container before it arrives. It also prevents losing containers or placing them in two stacks at the same time. In practice, this is the basic conservation rule that makes the plan executable. This slide introduces the stack capacity constraint. It limits how many containers can be assigned to a stack at a given time. Operationally, it is the physics rule of the yard. Without it, the optimizer could pile an unrealistic number of containers into one stack to reduce blocking on paper. Stacks have a maximum height capacity. Without this constraint, the optimizer can pile unlimited containers into one stack. Capacity constraints preserve physical feasibility and safe operations. They also protect realistic crane work, because stacking beyond capacity would force illegal moves or unsafe configurations. This slide introduces the blocking relationship constraint. It defines when one container is considered to block another based on their stack position and retrieval order. Operationally, blocking is the reason reshuffles exist. A later retrieval sitting above an earlier retrieval creates a future conflict that must be resolved by extra moves. This constraint activates a blocking indicator when two containers occupy the same stack across tiers. It is restricted to cases where retrieval time order would make blocking harmful. This is the bridge from physical stacking to future reshuffle decisions. It lets the model identify exactly which placements create future rehandling. This slide introduces the reshuffling trigger constraint. It links a detected blocking relationship to the requirement that a reshuffle must occur at the time of retrieval. Operationally, it prevents a common modeling failure, recognizing blocking but not charging the plan for the work required to fix it. When a container blocks an earlier retrieval, the model must count a reshuffle. Without this trigger, the model could hide blocking without paying for it. This makes the objective meaningful and enforces operational realism. If you want to minimize reshuffles, the model has to count them whenever blocking occurs. This slide provides a node-based stack illustration showing movement of blocking containers. Use this visual to ground the model. Every time the formulation marks a container as blocking, you can picture the physical sequence. Lift the top blocker, place it elsewhere, repeat until the target is exposed. This example makes the model concrete. Container A arrives at time 1 and is retrieved at time 8. Container B arrives at time 2 and is retrieved at time 6. Container C arrives at time 3 and is retrieved at time 4. Container D arrives at time 4 and is retrieved at time 7. With two stacks of capacity 3, an optimal plan places the earliest retrieval container on top and the latest retrieval container at the bottom. The result is one reshuffle versus 4 reshuffles under a naive first-come, first-served placement. Tier 2 uses a greedy heuristic. For each arriving container, evaluate each feasible stack and compute a blocking penalty. Then place the container where the predicted future blocking is minimal. Operationally, this is a fast rule you can use online when you cannot afford to solve a full integer program. This slide focuses on time complexity. The key drivers are the number of containers, the number of stacks, and the maximum stack height. Operationally, complexity determines whether the method can be used in real time. If decisions must be made continuously as containers arrive, the heuristic must run fast enough to keep up with operations. This slide shows the decision process in the minimum blocking heuristic. The operational flow is: observe the current yard state, evaluate candidate stacks, compute the blocking penalty for each option, choose the best placement, and update the yard configuration. This slide continues the heuristic description. Focus on how the heuristic evaluates a placement option and how it translates a placement into expected future blocking. Operationally, this is where the heuristic encodes yard intuition. Avoid placing late retrievals above early retrievals, because that creates predictable future reshuffles. This slide continues the heuristic description with the next part of the process. Operationally, the key is iteration. The yard state changes after every placement, so the heuristic must repeatedly reevaluate penalties based on the updated configuration. In this example, 6 containers arrive with retrieval times 12, 5, 8, 3, 10, and 7. 3 stacks with height 3 are available. The reported placement yields 3 reshuffles compared to 8 under random placement. That corresponds to a 62.5% improvement, illustrating how a simple greedy rule can remove a large amount of waste. Tier 3 searches over placement strategies using evolution. A chromosome encodes the stack assignment and position for each container. Fitness is the number of reshuffles observed when simulating retrieval. Operationally, this lets you explore a larger search space than a greedy heuristic, at the cost of more computation. Selection uses tournament selection with size 3. Crossover is order-based to preserve feasibility. Mutation is random relocation between stacks. Elite preservation keeps the top 10% each generation. Operationally, these operators balance improvement with diversity so the search does not get stuck too early. This slide shows the genetic algorithm evolution process for container placement. Operationally, the loop is: generate candidate placement plans, measure reshuffles under retrieval simulation, keep better plans more often, and iteratively improve the population. This slide is a code segment for the genetic algorithm implementation. Operationally, focus on how the solution is represented and how fitness is computed. If fitness does not reflect real reshuffling work, the algorithm will optimize the wrong behavior. This slide continues the code implementation. Operationally, pay attention to how the algorithm enforces feasibility during crossover. A plan that violates capacity or duplicates assignments is not useful, even if it looks good numerically. This slide continues the code implementation. Operationally, focus on mutation and iteration control. Mutation prevents premature convergence, and iteration control determines how long you allow the search to trade time for quality. The reported experiment uses problem size 50 containers and 8 stacks. Population size is 100 and generations is 200. The crossover rate is 0.8, the mutation rate is 0.1, and tournament size is 3. Operationally, these parameters describe how aggressively the search explores versus refines. The comparison reports that random placement yields 187 reshuffles in 0.01 seconds. A greedy heuristic yields 94 reshuffles in 0.15 seconds. The genetic algorithm yields 67 reshuffles in 12.3 seconds. The reported improvement is 64% over random and 29% over greedy, showing the speed versus quality trade-off. Tier 4 models placement as sequential decision-making. An agent selects a stack for each arriving container. The agent learns to reduce future reshuffling by predicting long-term impact. Operationally, this helps when the environment is uncertain, and the agent must learn patterns from experience. The state includes current stack configuration, plus global features such as time and remaining containers. The action is to choose one valid stack with remaining capacity. This framing enables learning under uncertainty in arrivals and retrieval requests. Operationally, it matches how placement decisions are made, one container at a time. This slide introduces the reward function used for learning. Operationally, the reward function is where you encode what good behavior means. If the reward does not penalize blocking strongly enough, the agent may learn fast placements that create expensive future reshuffles. This slide shows the reinforcement learning framework for container placement optimization. Operationally, think of the loop as: observe the yard state, choose a placement action, see the new yard state, and receive feedback. Over many episodes, the agent learns a policy that reduces reshuffles. This slide is the first part of the deep queue network implementation. Operationally, focus on how the state is encoded and how actions are restricted to valid stacks. If invalid actions are allowed, training becomes unstable and results become misleading. This slide continues the implementation. Operationally, pay attention to how experiences are stored and sampled. The agent learns from sequences of decisions, so training must expose it to both good and bad outcomes. This slide continues the implementation. Operationally, focus on how the network is updated. The model is learning to score placement options based on long-term reshuffling impact, not just immediate convenience. This slide continues the implementation. Operationally, this is typically where exploration behavior is controlled. Early exploration helps discover better placements, while later exploitation stabilizes performance. This slide continues the implementation. Operationally, this is where training loops and evaluation checkpoints matter. You want to confirm that improved metrics correspond to realistic yard behavior. Training data consists of 10,000 placement episodes with varying arrival and retrieval patterns. Results are reported after 5,000 training episodes. Metrics include average reshuffles, success rate, convergence, and adaptability. Operationally, you need both performance and reliability. A policy that fails under minor changes is not deployable. The reported metrics are: random policy has 45.2 average reshuffles and 60% success rate. Greedy heuristic has 28.7 average reshuffles and 85% success rate. Genetic algorithm has 22.1 average reshuffles and 90% success rate. Deep Q network agent has 18.3 average reshuffles and 94% success rate. Reported reduction versus random placement is 59%. Reported improvement versus greedy is 36%. The agent also shows high adaptability during online learning phases. Operationally, that adaptability matters because retrieval patterns and schedules change in real terminals.